So, thank you so much indeed for inviting me to the first ever inaugural, or depending on your viewpoint, second coming of MQ Summit. We were chatting last night about MQ Summit. There was an MQ Summit before. We didn't know about the MQ Summit before, so everything's a bit confusing. Anyway, I thought, what am I going to do for a keynote? What am I going to do for a keynote? Well, obviously, my first thought was I could explain to a room of people that know how message brokers work, But that would be an utterly waste of my time, because you know better than I do about how brokers and things like that work. And for a lot of my career, I've sort of focused on helping people ship software more quickly. That was the whole kind of driving force behind me getting interested in microservices. So I wrote some books about microservices. I enjoy the process of writing and helping explain ideas. And despite what I wrote in these books, people then went and built microservice architectures, despite the fact most of these books are about how these things are awful things that you should never, ever do. And as a result of lots of people now building microservice architectures, we've now got issues with systems not being quite as robust as we'd like. And so I started writing a new book all about how microservices are terrible, and actually distributed systems are terrible, and won't somebody please think of the children. I actually have a whole chapter on how message brokers work in there. If you want to have a look at that, it's in early access right now, and you can see how wrong I've got it, because this is a room of experts. So I thought there's no point in me going deep into the area of messaging, because you're going to have an awesome lineup of talks that are going to do exactly that. So instead, I thought I'd do a talk about what words mean. And as someone who writes and tries to make my words clear, and I try and be precise about terms, I thought this has been something that's been interesting me for a number of years, and I've got a talk that kind of covers this from the viewpoint of, well, this world we're operating in. And the magic word was actually mentioned in the lead up to all of this. I spend a lot of my time talking about boxes, right? And sometimes the size of the boxes is what's important. Like, should the box be big? Should a box be small? Should the box have other boxes inside the box? Probably should have other boxes inside the box. I spent an awful lot of my time talking about the shapes of the boxes, right? And I'm very much in Team Hexagon here. Shout out to Alistair Coburn and the hexagonal architecture pattern as a precursor to how we think of microservices. But this talk is much more about the more interesting aspect of any architecture, which we say is boxes and arrows. The boxes are actually less interesting than the arrows. And so I get asked a lot about the arrows. How do we implement the arrows, Sam? What are the arrows? How do you make them work? And so when we think about that classical microservice architecture, when I draw the arrows, it's probably worth, again, trying to be clear about what I'm showing. When I show an arrow between two hexagons, I'm showing effectively a sort of logical dependency. So I'm sort of showing that, one service at runtime needs the help of another service to do something. Okay, and the secret with a microservice architecture has always been, how do we make that work in such a way to reduce coupling and therefore allow these things to still be independent, which is kind of an ongoing challenge. What's the loosest form of coupling that we can get away with in the context of a service architecture? So in this example here, I'm showing that the return service needs help from the shipping service to make its job possible. So then when I'm doing classes, I'm working with clients, the next conversation that comes up is obviously, well, should this communication be synchronous, or should this communication be asynchronous? And I've always struggled with this. And I realize after spending a lot of time, and by a lot of time I mean like the last sort of 10 to 15 years working in this space, with this distinction. And in the end, I end up gravitating more towards trying to talk initially instead about the difference between request response and event driven, purely because I think this distinction is actually quite clear. And from a logical modeling point of view, quite important. But that still didn't satisfy me entirely, because that's not where people start their discussion. They start synchronous, asynchronous, synchronous, asynchronous. Or worse yet, they've already picked technology, and now they want to reverse engineer their chosen architecture into that technology, but I digress. So this is my happy place to have the conversation in, but people still want to talk synchronous, asynchronous. So I had to get to grips with why I didn't like having that conversation. And the reality I came up with is that there is no consistent definition of what asynchronous communication means, to the point where I think the term asynchronous is effectively meaningless in the context in which we use that word. And I was sort of inspired to write this talk by this awesome newsletter post by Pat Helland. Pat Helland helped pioneer the concept of eventual consistency. And he wrote a blog post reflecting on the fact that the term eventual consistency is actually quite confusing to people, largely because we use the word consistency to mean very different things in quite closely associated contexts. And so here's the proposal in this post, was that we should rename it eventual convergence, because it's still a good description of what's going on, but it avoids some of the confusion. So I thought, well, look, Pat Helland is not entirely sure what's happened there. We seem to have lost what's going on. That's strange. Anyway, again. So I thought, well, Pat Helland is sort of one of the smartest people in computing. I can be like a little bit as smart as that. So why can't I try and come up with a better name than asynchronous communication to fix this problem? Now, I'm going to give away the ending. Turns out I'm nowhere near as smart as Pat Helland, and I failed. But I'm going to take you through my failure in trying to understand what asynchronous communication is and maybe some different things we should do. To give you an idea of how long I've been looking into this, I put this on Twitter, a post a while ago saying, I'm not sure that I fully understand what asynchronous communication means. I think the definition is a bit fuzzy. And this was Twitter. This is pre-acquisition. This is back when we went out to call it Twitter, back when I used it. And I said, kind of help me. And I had a whole bunch of people that came back, sort of experts, that people I know and whose books I've written have came back to me on this, and just other people that I hadn't met before that had some really great insights. And I did my own research. I'm going to take you through what I found and see if we can come up with some of the observations based on this. I mean, what I found may shock you. I don't think it will shock you, but I had to put that in. The first response that came back quite quickly was this comment from Darren Hobbs, happened to be an old colleague of mine from my ThoughtWorks days. And he said that for him, asynchronous communication versus synchronous communication is a difference between sending an email and a phone call. Now, at one level, this sort of starts to make sense, right? If we think in terms of asynchronous communication versus synchronous communication between people, this distinction feels useful, right? Thinking about the interactions you can have via, say, email or maybe some Slack communication versus actually picking up the phone call. There's an immediacy to personal synchronous communication. However, applied in a computing context, this does sort of start to imply that asynchronous communication might somehow be slower than a phone call, which we know isn't true. But there's something interesting in there. Okay, that's interesting. So the Twitter thread's going on at this point, and I'm going through all the tweets, and I thought, well, I should look elsewhere. So I start looking at other sources of where people may have gone out of their way to define terms. And so I looked at the Reactive manifesto, the second version of the Reactive manifesto, because the first one wasn't great. Hands up, anyone here that's actually read the Reactive manifesto? Keep your hands up if you understood everything in the Reactive manifesto. Okay, most of the hands have gone down. Now, actually, I need to be very clear. Some of my friends wrote this, people who I respect very much, and who, in many cases, have incredibly smart ideas. I'm very much, when I poke fun at this document, I'm going to be very much punching upwards, or at least across. But I say it with love, because there is still good ideas in here. I mean, you have to view the Reactive manifesto as a piece of dogma, which isn't to say that dogma is always bad. It's just this is a very specific viewpoint about how systems should be built from people for whom which these ideas worked really well. That's not the same thing as saying this is a universal model of how we should build systems, but they've made an attempt to define terms, and I appreciate that, and I thought, great, let's take a look at it. So we go through to their definition of asynchronous, very helpfully linked. We'll come back to that Oxford Dictionary defines asynchronous as a bit later. There's a term there, but here we go. We get into their definition of asynchronous communication. Asynchronous means the processing of a request occurs at an arbitrary time, sometimes after it has been transmitted from the client to the server. So that's their definition of asynchronous. And some of you are nodding, thinking, yeah, that sounds good. And I looked at this and thought, this is rubbish. What does this actually mean? Because, of course, that's how it works. How else am I going to process a request? It has to be after it's been received. I can't process a request before it's received, right? That's some kind of Doctor Who type level stuff, right? That's like I've got some kind of networking protocol that can travel in time. So that definition of asynchronous to me was not helpful, because I'm always going to process something after it's received. So that's not actually a helpful definition. So I keep digging deeper. Now, thankfully, they actually had some other definitions of the word synchronous. So I thought, well, maybe their definition of synchronous is helpful, and I think it is. So this is the opposite of synchronous processing, which implies that the client only resumes its own execution once the service has processed the request. This is about something a lot more specific. And although this might not be the definition of asynchronous that many of you in this room know, this is actually probably in many ways the definition of asynchronous that most programmers are aware of when you use the word asynchronous. This is something very, very specific. So this actually came back on a Twitter thread. Steve Smith is a friend of mine in the UK. You know, he originally said, okay, so for him, the difference between synchronous and asynchronous communication is that synchronous communication means that I've got a TCP connection open for the duration of the communication, right? So of me, of course, being a pain in the bum, I suggested, so if I use a different networking protocol, what does that mean? Which of course, Steve knows me, so I come across like an idiot here, and I am, but Steve also knows me, so that's okay. And he says, what he actually meant was, I assume you're not blocking for a response. So there again, we're starting to get into more specific terms. This is coming back to how the Reactive manifesto thinks about this. So blocking for a response. So let's go to the Bible. Not in literal Bible. We actually will go to the Bible later. Let's go to the Bible of Distributed Systems, which would be Tannenbaum, specifically the third edition of Distributed Systems by Tannenbaum and Van Steen. It's freely available online, by the way. The paper copies of this are extortionately expensive, but it's still great. Tannenbaum uses the word asynchronous very sparingly. In what is a 600-page book, there's probably less than 30 references to the word asynchronous. And most of that is in the context of talking specifically about the use of 0MQ as an example of a protocol. So kind of Tannenbaum recognizes this word isn't that useful. But this is at least a good definition from Tannenbaum. The characteristic feature of asynchronous communication is that a sender continues immediately after it's submitted the message for transmission. So all these three definitions from three different sources are not talking about anything to do with queuing or anything to do with middleware. They're talking specifically around this concept, which is called non-blocking. So, quick primer for those of you who aren't aware of non-blocking. What does non-blocking look like? Let's take a simple scenario. I've got a service that needs to accomplish some tasks. What we've got to do is we've got to award some points. We've got to go to the loyalty service and say, please, can you award some points? And I've also got to go and upgrade a subscription. These are two jobs that need to be accomplished. They're not sort of, one doesn't have to happen after the other from a business process point of view, but just from an implementation point of view, that's kind of how they've been implemented right now. So we can imagine a kind of a fairly naive piece of code like this. In this example, we're using some kind of RPC abstraction over the interactions. So I start off by saying, okay, my first thing I'm going to do is I'm going to go to loyalty service and I'm going to say, please award some points. So if this was, say, a HTTP-based comms, I'd open the connection, I'd send the request over, the processing we're done, and I'd be waiting for the response. This could also be a wrapper around a queue-based mechanism as well. We'll come back to that a little bit later on, though. Once that is completed, I then move on to the second operation and do this call to the subscription service. Now, as we can see, these aren't linked causally from the point of view of program flow. I don't need the result of the first operation before doing the second operation. So they are kind of independent, but we're treating them as something we're doing sequentially. So the issue with this, of course, is, well, fundamentally is that the latency for this operation is now going to be bound to being the sum of these two calls. So if the first call took 50 milliseconds, the second call took 150 milliseconds, the operation from the viewpoint of entitlement is now going to take at least 200 milliseconds. And this becomes an issue a lot with people using RPC-based abstractions because they're often unaware they're actually making service calls. I remember speaking to the folks at Netflix early on, and they had huge amounts of issues with this, with very smart developers not being aware that what they were doing was crossing a process boundary, things happening sequentially, and latency blowing out as a result. And so actually, certainly at Netflix, the reason they implemented their own reactive extensions, which is kind of what we're talking about here, was to bring this down. This is also a problem when we consider that latency is not fixed, latency varies. This is why we pick some broker-based implementations, because they give us more consistent throughput. But we have a range, and if you sum up all of these sequential operations, that range for an operation just gets bigger and bigger and bigger. And systems with a large range for latency are an absolute pain in the bum to operate, because it's very difficult to know when are they healthy, when are they not healthy. Now, a significant improvement here would be to instead obviously do these calls in parallel. So rather than doing call 1 and then call 2, because at each point we're blocking and waiting, we make the next call, we block and we wait. So we've got that single thread of execution is blocking and waiting all the way through. Instead, let's do them both in parallel, right? Nice and easy. So that's what we want to try and do. Most of the ways you then implement this from a coding point of view, you're using some variation of a reactive extension for your programming language of choice. .NET really had the first good implementations of this, because that's where those ideas were pioneered. Underneath all the syntactic sugar, the way most of these things work is by making use of something called a future. So a future here is a read-only type, the value of which may be available, well, will be available at a point in time in the future. So it's like it's a dead cat in a box, basically. Just has the dead cat died yet? This is all quite grim, but I probably shouldn't have used that analogy. But the idea here is that when we execute that first line of code, what actually happens is the content in the parentheses there, it's not like we block and wait until that's completed. What's actually happening is there'll be some syntactic sugar that takes that call and say in a JVM-based system, would stick that in a thread that's going to get executed behind the scenes. So when that line of code executes, all that we know is that this piece of work has been scheduled and is going to be done, out of band effectively in a separate thread of execution. So that's really nice. And now our piece of code, we could run through a whole bunch of these calls without blocking execution. So if you think about this thread might also be involved in, say, user interface updates, we can keep UX more lively. We can also make things operate in parallel much easier. So this is a nice, simple, easy change to make. And again, the syntax and the language may change for your programming language of choice, but the similar idea is going on here. So this seems good, right? So now we've made these calls operate in parallel. We're not blocking client-side execution. So according to Tannenbaum and the Reactive manifesto and my mate Steve, we are now asynchronous, for some definition of the word asynchronous. The problem comes with non-blocking is that sometimes we actually need the answers. We actually need the responses. Okay, because if you think about at this point in the code, at that point, all we know is that these two calls are going to be scheduled. They may or may not have completed by the time our code gets to that point. In fact, they almost certainly wouldn't have completed, just thinking about how quickly this will operate. And so if we actually need the answers or not, we have a problem, because we don't know at that point whether or not the value of the future has been computed yet. So we're like, well, what do we do? Well, we wait for the results. And that's when you'll see something like this, an await. Often, these two things are combined together into an async await, is probably what you've seen. What does an await do? It blocks, waiting for the results. So non-blocking is useful, but you do actually end up still having to block when you need answers. If you don't need answers, and you don't care about the answers, you don't have to block. If you need the answers, you need to block. This might be to make sure it's happened, or because you need the result of that operation to do the next piece. So, not to say that non-blocking isn't useful, it is absolutely useful, but the logic of your processing might still require that you wait for things to happen. So it's not as simple as just sprinkling in some non-blocking client code and thinking now non-blocking. You might actually need to restructure how your business processes are implemented, because otherwise, even non-blocking calls end up blocking. Still, this is still, if you're in a situation right now where you're doing communication like this, it's still a good idea to use these, because there's also a lot of nice syntactic sugar. And I've given you very simple examples here. I've removed things like retry handlers and error handling and all those sorts of things. So this is going on. This conversation still happened on Twitter. So somebody else came in and said, well, for them, synchronous communication, is there a direct communication between the sender and the receiver? This kind of is almost touching on some implementation time coupling. Think about HTTP-based connection, for example. We have that established connection between the two. But here we start to see, coming in from Benjamin, who's a person I didn't know, there is an intermediary involved between the sender and receiver. For example, the message broker. So this word of an intermediary starts coming into the conversation, and Benjamin is talking specifically about a broker. And intermediaries have often been used to make the interaction asynchronous, right? So rather than going from A to B, I instead give it to a broker or some other intermediary, and then the idea is that when B is ready, it is able to take delivery of that message. The reason we like message brokers is that message brokers do lots of smart things for us around guaranteeing delivery. Now, there are some message broker vendors in the room, so I'm going to say the ones of you who put your fingers in your ears. For the rest of you that aren't message broker vendors, message brokers vendors will then say, we do guaranteed delivery. There'll be a big asterisk next to guaranteed delivery. There'll be about 30,000 pages of design documentation explaining how they do guaranteed delivery for you. You probably need to read those docs, all right? You can unplug. For the rest of you, brokers are magical things that just always work, and you don't need to worry your pretty little heads about it. But you do need to find out how it works. Anyway, so we go back to Twitter, and I like this one. It's someone else I didn't know. Async is like dropping snail mail in a red post box. and then going on with your life. And this is sort of, there's a little bit of, of a combination here of the idea of putting something in the message box and going with life. There's also a bit of a non-blocking idea here, right? I'm giving it to the mailbox. A mailbox is by the word Tannenbaum uses. He uses the word mailbox to describe this kind of interaction. And then going on with your life, right? And then bam, one day, Postman Pat stuffs something into your house mailbox, along with loads of coupons and charity mailers. I'm aware that many of you may not be aware of who Postman Pat is. This is Postman Pat and his black and white cat, Jess. When I was a kid, I remember Postman Pat. He was a little bit recent for me. I got to kind of tail end. The modern Postman Pat has a hovercraft. I don't really agree with. But Postman Pat, this is the mail service, right? I'm here. I'm not in my house. I know there's letters waiting for me at home because I have a camera. Because everyone has cameras now. And so I know the postman has been putting letters in my mailbox. When I get home, the letters are going to be waiting there on my doorstep, right? So that's a nice idea for me. Again, in the human world, that's useful. I did not have to be at the house to receive those letters. And that's a nice idea. This is kind of the mailbox concept from Tannenbaum, the idea that I can put them into this. Now, of course, we're thinking in terms of brokers, especially with this kind of conference. But there are lots of variations on intermediaries we can use to hold on to things until we need them. Okay, so we could use a database, for example. I mean, look. I mean, you can absolutely use a database table to store things that other services are going to integrate on. This happens all the time. I mean, Oracle sold Oracle MQ for many, many years that was just a JMS wrapper around a database table. The really depressing thing was it worked a lot better than many of the other Java-based brokers out at that time. What's the most common service integration mechanism in the world? Probably still today. And maybe outside of IBM MQ, probably still moves more money than anything else, file-based communication. This is how still most of the banks work. Yes, I know, like JP's Fed clearance system works on MQ, but like file system, right? One mainframe creates a file, puts it in a location that other things then pick up, right? It's not rocket science, it works. And despite what many of you will be hoping, it still works a depressing amount of the time. It's still there. A lot of these old systems that we can't replace, this is how they still work. We're using the durability of the file system to keep our things safe. Now, of course, we don't get any help around notifying us that things happen. It is lousy for low latency. It's great for high volume. You could use email as a way of integrating between services. You shouldn't use email as a way of integrating between services. I just thought I should put that out there. Hopefully, I shouldn't have to say it, but it's a terrible idea. But you could do it, right? It's not the only game in town. I mean, I didn't put atom feeds up here. And certainly, I've used atom feeds in the past for effectively as a mailbox mechanism. It's a bit of a blurring the lines, though. Coming back, we've got Twitter is still going. We've got Graham Lee. He's a friend of mine from Australia, worked at Tyro. He started off by saying the sending service doesn't wait for completion of the receiving service before continuing and or completing its own work. And that, again, is very much from the point of view of a client, is very much the non-blocking stuff. And again, the non-blocking concept came up more, actually, than the concept using brokers. But then he goes on to say, but the more I think about it, I also expect a temporal decoupling from the service's availability. So this is another kind of concept that comes in. I think it's really useful, this idea of temporal decoupling. Now, words get used and phrases get used in certain contexts. There's also a concept of temporal coupling at a code level. We're talking about it here more at the distributed systems level. Again, this is something that Tannenbaum does talk about. So what is temporal decoupling? When we talk about temporal decoupling, we're saying that the sender of a message doesn't need to worry about whether or not the recipient is currently available or not. And we normally use an intermediary to achieve this temporal decoupling. So if I have something that's temporally coupled, so for example, HTTP-based communication, for example, point-to-point, that I have to be able to establish the connection, send the request, and at the very least get an acknowledgement of receipt of that request for this operation to complete. And ideally, if we're doing request response, I would also need to make sure the response comes back. Now, if at any point during the operation the shipping service becomes unreachable, this operation is going to not work. And if the operation doesn't work, now the client has to consider, well, do I retry? Do I buffer and delay that retry? Or do I cascade the error back up? So as the system becomes more distributed and you have more moving parts, you start becoming more aware of the fact that arbitrary partitions sometimes occur and they're not always under your control. And so this temporal coupling becomes a source of retries. And retries can always be a little bit problematic in a system. That's definitely a talk for another time. So instead, it would be nice if what we could do is say, OK, let's put the message in a mailbox. This is our intermediary. And so when the shipping service is available, it can take that out. And we've now temporally decoupled returns and shipping, of course. And so now we don't have a single point of failure, which of course is a lie, because we've just shifted our reliance now to the mailbox. Right, so now our hope is that our intermediary mailbox vendor of choice does a better job at maintaining availability and durability than we can for our own services. So again, MQ vendors, I'm looking at all of you. This is now your job, right? Because this thing has to be reachable. All that stuff we talk about having to do retries and back-off policies and everything else that we would otherwise have to write as a service implementer when using, say, HTTP, the message broker libraries do for you. Right? So the work is still being done to establish that connection. It's just we are abstracted from it. And the reality is, look, message broker vendors spend all their time thinking about this stuff. They will do a better job than people who are just building service-based architectures. That's the whole point of getting smart people to write complex software for you. So this then moves on to different types of interactions. So a lot of the time when I'm doing my comparison between request response and event-driven, I see people immediately think request response equals some sort of TCP-based direct comms, point-to-point comms, and they won't think of anything else outside of that. And so I would try to get people to think more broadly. No, you can run request response over queues. And in fact, this is a mechanism for interaction that's actually more prevalent than event-based systems in my experience anyway. So we have a service. I have a queue. I put that request on that queue. And then when service B is available, it picks up the request. And then when that work is done, it sends the result back. And that's nice and simple and straightforward. This works really well. And I bring this up because people often think, oh, I've got to be event-based and stuff. I'm also using the word queue here. And again, this is going to be sacrilegious. The differences between a queue and a topic from the point of view of this conversation don't matter. I know some of you are going to be really annoyed at this. No, it's not that you're angry. Kafka is saying they can do queues. It doesn't matter for most people. They don't care. It's a reliable mailbox, all right? So a reliable mailbox, passing this stuff around, this works really, really well. Now, it's great when I start working through this sort of stuff with teams, because it starts creating new sources of challenges, and we start to think about the interactions between things. Because we also know that, in reality, we've probably got multiple instances of our services, which is a very common thing to do for certainly robustness reasons, if not also for, scale reasons. And so, if I send that request, and I've got a response that wants to come back, that response could easily end up being received by a different recipient, right? Now, some people see this as a massive problem. There'll be middleware vendors out there that will sell you solutions to help route calls back to the originating sender of that. That would be a mistake. The problem with this is people write code in such a way that they expect the response to come back to the same instance because they are retaining state in memory required to continue processing. This is what we call stateful processing. Processing things statefully is more complicated to implement if you actually care about things working. The problem is if I'm doing stateful processing, what happens if the node doing the stateful processing fails? Well, I've lost that in-memory state. But that's fine. I will use a complex Baroque solution from another vendor that I have to pay for to replicate state between the nodes. Well, now you've got another problem, right? This is another source of complexity. I've had two separate major production outages caused by replication of in-memory state for stateful processing. One on a Java stack, one on a .NET stack. The other issue then we have is routing. That response has to go back to the instance that sent it. So now this is why we do things like sticky session load balancing, for example, is because people are using in-memory session state because they never read the thing about what cookies are for. So you probably do not need to do stateful processing. If you're a message broker vendor, yes, you do need to do stateful processing. You are exempt. You can set out as part of the sermon. Stateless processing means that when you get given a bit of work to do, could be a response, could be a request, could be an event, could be a message, whatever, everything you need to carry out that processing, all the context you need is in the thing you're given. You can still fetch that from a database, that's fine, but we're not trying to keep hold of in-memory state. trying to build stateful processing systems. It is complicated to do. It is very difficult to scale. Just don't do it. And if you really think you should be doing it, then you're not going to listen to me anyway. But I've fixed so many systems like this. So this scenario here, actually, this interaction model actually encourages us towards stateless processing. So now we're thinking differently. How can we build our system in such a way that any of these services could pick up that response and carry on the processing that we might require? And often the answer here is, well, we've just actually saved enough of the state of where the processing was into a database so we can carry on that processing later on. So I actually think using brokers for request response sort of it becomes a forcing function. It encourages stateless processing. Whereas we come back to our example from earlier and we think about the statefulness of our processing. Here we've got this assumption that the response always comes back to the thing that sent the requests. And again, if this was HTTP-based communication, that just happens naturally. I've opened up a TCP-based or a QUIC-based connection between the client and server. The response has to come back over that pipe. That's just the world, right? So instinctively we understand that, and that's how we kind of write our code. It then gets interesting, though. So if we think about when we've created these futures, before those futures have completed, what happens if our service fails? That enrollment service is taken offline. Maybe it's affected by, I don't know, US East 1 or something. Whatever, it doesn't really matter. It just goes, right? So when it's gone, what's happening to all these calls? These calls are probably still going to be carried out. But this is probably related to an overarching operation that we probably want to complete. Often the answer is then, well, we'll just retry the whole thing, in which case you have to make sure that those two operations we highlighted earlier have been implemented using some sort of idempotency keys or similar. And in the past, I wouldn't have good answers for people who would write code like this, especially with HTTP-based comms and sort of orchestrated business processes, largely because the solution in this space historically would have been to use some kind of heinous BPM solution. Right, the vast majority of which were horrible and expensive and hard to work with, and in some cases involved using JSON, which I won't do. Nowadays, actually, in these sorts of scenarios, I've become actually quite a big fan of temporal. So I think if you're looking at orchestrated workflows, it is absolutely worth a look. The reason I tend to like temporal over some of the old school BPM solutions is it's very light touch on your code. So you can just have a piece of code that implements a step in a process. You can just annotate it, and the temporal workflow makes sure these things work. 100% is compatible with you using queuing for communication between those things as well. So it is worth a look. And I've spoken to people, some big .coms, who are very happy with it. So it's worth a look if you're in that kind of space and you want that reliability that the processing is carried out, especially if you are in that kind of world of more direct HTTP comms at the moment. So we've got a bunch of competing definitions we've looked at. We've talked about this idea of immediacy. Does asynchronous mean slower or not? I don't think it does. We've got temporal coupling or temporal decoupling, more to the point. We've got this concept of non-blocking. We've talked about the intermediary concept in general. So it's like, well, which one of these definitions for asynchronous communication is right? Which one do we pick? Which one do we pick? And of course, the next question to ask is, does it really matter, right? Words do have different meanings. I appreciate that for the vast majority of the people in the room, English is not your first language. And for those of you who did learn language later on in life, I am sorry. It's not my fault. But it's not a very consistent language, right? We have lots of words that mean different things in different contexts. Now, we've got a small enough audience, I can do a bit of a poll here. So if we look at the English, the actual Oxford English Dictionary, which is effectively our kind of definitive definition of the English language. This is the big, huge, like 60-volume edition. Does anyone know which word in the English language has the most definitions? Pardon? Run we'll come to in a minute. What else? There's another. In the current edition, see, I'm being very anal now. You'll get to talk about it. What's another word? Pardon? No. Well, yeah, you'll like this from a programming point of view. This is quite fun. In the current official edition, set has the most definitions. Do you know what's quite close behind set in terms of having the most number of definitions? Get, which I really like as a programmer, right? You know? But you're right, in the new edition that's currently in draft form, run has the most definitions. The next edition, they reckon, will be complete in 2037, which gives you an idea about how long they spend doing this whole process. When I say lots of definitions, let me put this into context. Set has 430 discrete meanings in the Oxford English Dictionary. Run, in the current draft, at least when I looked last, had 645 different meanings. And this is reflecting the fact that we use words and the way we use words changes. So we get used to this. Run has loads more definitions. Actually, a lot of the definitions for run come from the world of IT, which of course was not around when the previous edition was sort of finalized back in the 80s. So we are kind of instinctively used to words having different meanings. And the reality is that we derive our understanding of a word from our personal context and from the context in which those words are used. I was having this discussion with Ian Cooper a few years ago. Some of you might know Ian, and it wouldn't surprise you to know that Ian has a hinterland. We're not designing RPGs in his spare time. He also studied semiotics at university. So semiotics is the study of meaning. And so this is paraphrasing something he said to me. He says, the meaning of a word becomes more narrow as we put other words around it. As we put words around another word, we are giving it context, and it becomes easier for us to understand what that word means in isolation. So we'll do a little test. So let's come back to that word run, right? This one that's going to have all those definitions. I want each of you in your minds to think about just one definition of what run means to you. Just pick one. Just think about that for a moment in your head. The issue got worse the moment the program was run. Did my definition of the word run match yours? For some of you, yes. Some of you, no, right? Try again. Think of a different meaning of the word run. Think about what that might be in your head. One definition of the word run. The economy crashed due to a run on the banks. Another definition. Maybe some of you are worried about your portfolio and you might be thinking about this. Probably most of you weren't. They're both valid definitions of the word run, or uses of the word run. The versions in your head, they're all valid too. But you don't know which word we were talking about until we put other words around it. That's how you derive the meaning. We need other words around a single word. We can't use most words we cannot use completely in isolation and expect everyone to understand what it is we're talking about. Context is really important. Let's come back to the Reactive manifesto. The Reactive manifesto does what often people do when they want to define a word. And my heart always sinks when I say the Oxford Dictionary defines so-and-so as, right, which is what they start off with. The Oxford Dictionary defines asynchronous as not existing or occurring at the same time. And actually, if you search for what does asynchronous mean into Google, you'll get this answer, right? If you put it into ChatGPT, you'll probably get an essay explaining why ChatGPT is great. I'm not entirely sure, but this is the first answer you get back from Google, as though there's one definition of that word. And it is, when I say the first answer, I mean it is literally the first definition there is for asynchronous in the Oxford English Dictionary, because it's the first citation of when that word was first discovered. You can go and look at the full dictionary up. It's online. So it's literally the first one. Now, the Oxford English Dictionary does actually give us context. It explains where these words came from. And so we can look at the context in which this word was originally used, this phrase was used, and it was originally only used in medical contexts. So my friends who wrote the Reactive manifesto have picked out the word asynchronous from the context of used in medical procedures and used that in computing. But that's because there are no definitions for asynchronous in relation to computing in the Oxford English Dictionary, aren't there? No, there are two. Neither of them actually are helpful. The least unhelpful definition is this one, which is designating transmissions in which packets of data are sent at irregular intervals, with the start and end of each packet being marked by specific signals involving such transmissions. I don't know what that means. It's valid, though, in the context in which this discussion was done. And remember, this probably is going to be coming from the 1980s, so I'd imagine this was discussions, and you can actually go to the citations. It makes perfect sense to the people who use that word in that time. It does not make sense to us. Why is all this important? Because fundamentally, the systems that we build and the software we construct, they are socio-technical systems. So to break that word down, socio-technical. Socio means people. Right? It is human beings working together. And technical, this is kind of the old-fashioned definition, or the old definition, or the original definition of technology, as in techne, meaning knowledge and processes. And we now, in a modern context, would also infer this to mean the software and hardware we used. When we build systems, we are bringing these things together. The area of research around socio-technical systems is actually long and storied. And before you think the term socio-technical is some sort of left-wing, wake, liberal snowflake nonsense, the concept was originally developed when looking at the efficiency and efficacy of coal mining during World War II. It's actually work done by the Tavistock Institute in London. We're looking at coal miners. How can they be safer? How can they get more coal out of the ground? Very important for the war effort at the time. And so this field of study emerged from their work. You'll also find references to the Tavistock Institute as being involved in a conspiracy theory during the 60s, as some people thought that the Tavistock Institute had created the Beatles to help overthrow Western civilization. Not even making that up, that was a legitimate conspiracy theory in the 60s, and all I can say is if it was true, it's taken quite a long time to have borne fruit. But the reality is, the reason that talking about socio-technical systems is important is because the amount of software created that's valuable by individuals is vanishingly rare. Vanishingly rare. Like Linus created the kernel. He created the first version of the kernel. His biggest benefit, the thing he's done most of, is helping lots of people work together to create the software together. Most valuable software is not created by individuals. This idea of the hero programmer is kind of it's a barren concept. So bringing people together to build a system together requires that they can talk and can communicate with each other effectively. If you've got two different people that have very different definitions of the word asynchronous or similar, they might have very different pictures in their heads about what kind of system you're going to be building together. And this can then, of course, fall apart. I did promise a biblical reference. This problem of communication and being on the same page, this is not a new idea. We can think of the Tower of Babel, an Old Testament story which speaks to the people of Babel who were constructing this grand tower. And in the King James Version, there's actually two reasons given to why they were so effective at creating this tower. We remember the fact that the reason they were able to construct this massive edifice was because they all spoke the same language. They also, by the way, in the Old Testament does mention the fact they had good technology. We kind of skip over that bit, which I find odd. And then for reasons that's not expanded upon in the original Old Testament translation, the Old Testament God said, don't like that, and made them speak different languages, right? There's interpretations to why that was done. It's not really explained. But we understand the impact that had. This is, whatever your belief systems might be, this is a very, very old story that's been around for thousands of years. We understand that if we can speak the same language and use the same words and use the same terms, we can do bigger things together. And when those words and meanings are fractured, that undermines our ability to work together. I come back to this fact that the word asynchronous, even in the narrower context of inter-process communication, it has so many different meanings that it is meaningless. When Tannenbaum himself just avoids using it as much as he possibly can, I start to pay attention. So what can we do? I didn't come up with a unifying word because I realized there isn't a unifying term because it does mean very different things. So if you're an application developer, start by thinking not about synchronous, asynchronous. Start from the viewpoint of what's your application need to do? How should it handle different situations? What do we want my application to do when a server is unreachable? How do we want to handle that scenario? Because that is one of the potential problems in a distributed system. The thing you want to talk to may not be there. So when it's not there, what are you going to do about it? How do you want to be able to handle that scenario? Explain it. Have a conversation amongst yourselves. There's a technical conversation there. It's having a business conversation to have there as well. How fast do we want our application to be? Right? Is speed important? In which case, how fast does these operations need to take? What do we do if a client crashes rather than if a server is unreachable? How do we want to handle those scenarios? Because that's possible. The client crashes, what am I going to do? And when you're answering these questions, try and use much more specific, explicit terms. Say our clients are going to be non-blocking so that we can, for example, run operations in parallel. We're going to be using a message broker as an intermediary so we can achieve temporal decoupling or whatever else it might be. I would just caveat this by saying, try not to make having a common meaning about being correcting other people necessarily. Your definition is wrong. It's not wrong. It's just their definition. What you need is a shared definition. The running joke in The Princess Bride, of course, is that Vinicus keeps using the word inconceivable in a way that nobody else really thinks is how that word is used. And then Guillermo Montoya is very polite and very nice. He said, don't think that word means what you think it means. He's trying to help, right? He's being nice about the whole thing. And of course, you have to remember The Princess Bride is understandably a comedy, not a playbook on how to deal with interpersonal relationships on a client, on a project, right? So if you're not sure that you're talking the same language, if you're not sure that terms are being used in the same way, rather than making assumptions about what you think the word means ties up with what they mean, just ask the question. So when someone says we should make this asynchronous, say, what does that mean to you? Pictures are great. Having conversations is really important. But don't make assumptions about what that word means to people, because it means things very, very different. Anyway, if you want to know more about the work I'm doing at the moment, you can go read the early access version of my book. I have a whole chapter on message brokers and how message brokers work. Please read that and correct me if you think that I'm wrong. I don't slam dunk on any brokers. I do a bit. Anyway, have a look in there, and you can get the slides for this talk, that QR code. There's also, we can find a link to my mailing list. You can sign up for updates and find out more about what I'm working on. But thank you so much for your time.